All right, in the last video we were very qualitative, and now we want to get quantitative. And we want to specifically quantify the amount of heat transferred between different objects. And we do that with heat capacities. So in order to quantify the amount of heat exchange between things, we're going to take advantage of what's called the specific heat capacity. So the specific heat capacity of a substance, often abbreviated as just the specific heat, is the quantity of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius, or 1 Kelvin, because when we're talking about temperature changes, right, the magnitude of a degree Celsius is the same as the magnitude of a Kelvin. And so the specific heat capacity is an intensive property. It doesn't depend on the total amount of the substance, it just depends on the identity of the substance. So it doesn't matter whether I have a gram of gold or a kilogram of gold or a ton of gold. It would always have the same heat capacity, or same specific heat capacity. And so the equation that we use to calculate the heat transferred is given here, where Q is, it's a different color, Q is the heat, and I'll get to units in just a second. M is the mass. The C with a subscript S, that is the specific heat capacity. And delta T is the change in temperature. All right, and so when we talk about units, there could be different units for the specific heat capacity, but the ones that we'll most often use are, the units will be joules divided by gram times degree Celsius. Or we could replace the degree Celsius with a Kelvin. And when we use the specific heat capacity in these units, that requires that we use specific units with the heat and the temperature and the mass. And so the heat has to be in joules, so it matches the specific heat capacity. The mass must be in grams, and the temperature must be in degrees Celsius, or Kelvin would also work, because we're talking about temperature changes. Another thing to remember, right, so that delta, right, so delta T means the change in temperature, and we'll use delta a lot. Delta just means change, so, we could have the change in anything. Here specifically we're talking about the change in temperature. And whenever we're calculating changes, we always do the final minus the initial. And that's particularly important when the sign of the change matters, as it does in this case. So you always want to remember to do the final temperature minus the initial temperature. Not necessarily the largest minus the smallest. Always the final minus the initial. So this is just a table of the specific heat capacities of a number of different substances, just to give you an idea of what kind of magnitude these specific heat capacities have. One thing I do want to point out is water has a relatively high specific heat capacity compared to a lot of other substances. So that's just a good information to have about water. It has a relatively high heat capacity. This is what it makes it good for being used in the radiators of our cars. It takes a lot of heat to cause that water to boil compared to other substances that we might use. Of course, we often don't use just water. It's often a mixture of water and ethylene glycol, which gives it an even higher heat capacity than water has on its own. So when we do calculations, we want to be sure that we're aware of the sign on Q, because it can be positive or negative. When a substance gains thermal energy, and so when the final temperature is greater than the initial temperature, then right, so the temperature is increasing, then the value of Q is positive. If a substance loses thermal energy and the temperature goes down, so the final temperature is lower than the initial temperature, then the value of Q is going to be negative. So again, when we're doing delta T, it's always important to do T final minus T initial, so we get the proper sign on delta T. And also then, therefore, the sign on Q. Alright, so I want to just finish up with a couple examples of the types of problems we might do, and then there's another video with yet another example. And so I want to know how much heat is lost when a 25-gram sample of water cools from 75.2 degrees Celsius to 24.0 degrees Celsius. And they give us the heat capacity of water. So the equation I want to use is Q is equal to MC and sometimes we leave the S off. Sometimes we write it. I'm often, when I'm doing calculations, just write C. I don't bother putting the CS. Um, and so I'm looking for the heat. And so I'm looking for Q. So Q is already isolated in this equation, so I don't need to rearrange anything. I just need to plug in my values. I could put everything into the equation. In this specific example, I'm going to go ahead and get delta T first. Right, so I'm going to do final minus initial. And so my final temperature is 24.0 minus 75.2, and both of those are in degrees Celsius. And so for delta T, I get negative 51.2 degrees Celsius. And so this is an example of where the sign is important, right? Because the temperature went down, delta T was negative, and so Q is also going to come out to be negative. All right, so now I'll go and plug everything else in. So my mass is 25 grams. My specific heat capacity is 4.184 joules per gram times degrees Celsius. And then my delta T is negative 51.2 degrees Celsius. And I just put the temperature in parentheses so I don't get confused and think that I'm subtracting. And if I check my units, right, the grams cancel, the degrees Celsius cancels, and so I'm left with joules, and that's good because I'm calculating the heat. And so when I do 25.0 times 4.184 times negative 51.2, my heat that I lost was negative 5360 to the correct number of significant figures, and the units on that are going to be joules. All right, one more example in this video. So here we're told an unknown metal sample weighs 526 grams, and this metal piece absorbs 5.28 kilojoules of heat. The temperature then increases from 23.2 to 34.8 degrees Celsius, and we want to know, could this metal be copper? So, right when they start talking about absorbing heat and changes in temperature, right, I'm immediately thinking about this equation. And if I remember that the specific heat capacity is a constant for a substance, it's specific to each substance has its own specific heat capacity, and that specific heat capacity doesn't change. And so if I can calculate that, the heat capacity of this unknown metal, I can compare that to the heat capacity of copper and make a determination on whether this could be copper. So there are a number of things I could do here. The first thing I might do is check my units on everything and see what I've got, right? So if I'm trying to calculate specific heat, I'm trying to find C, so I need Q, I need the heat, and I'm told how much heat it absorbed. I need the mass, which I'm given, and I need the change in temperature, which I can calculate. But in looking at the units, so the mass is good, it's in grams, the temperatures are in Celsius, and so that's good, but the heat is in kilojoules. And to use this equation, I need to convert that specific heat I need to convert that heat into joules. So I'm going to use that let's try it again. 1 kilojoule is 10 to the third joules. So I'll take my 5.28 kilojoules, 1 kilojoule, 10 to the third joule, so I have 5,280 joules. And then before I plug my numbers in, I'm going to go ahead and rearrange it and solve for C. All right, so I have Q MC delta T. And so I want to get the M and the delta T over on the other side. So I'm going to do that all in one step. So I'm going to divide both sides by M and delta T. And so I get C is equal to Q over M times delta T. All right, and I'm going to go ahead and do delta T first. So delta T is the final minus the initial temperature. So here my final temperature is 34.8 minus 23.2. And so for delta T, I get 11.6 degrees Celsius. So when I plug in my values now, I'll put 5,280 for the heat, and that's in joules. My mass is 526 grams, and delta T is 11.6 degrees Celsius. So when I punch that into my calculator, I get 0.865, and my units, nothing cancels out, and they're going to be joules per gram times degrees Celsius, right? And that's good. Joules per gram times degrees Celsius are the units on specific heat capacity, so that is encouraging. And so now what I would do is go to a table of specific heat capacities and compare this heat capacity to copper and see if they match, or at least if they're similar. And so I've got one of those tables on the next slide. So we calculated 0.865 joules per gram times degrees Celsius. And I find copper, right? Copper's heat capacity is 0.385, so that's pretty different from what I calculated. So, my answer to this question would probably be no. It is not likely to be copper. Now, the previous question didn't ask this. We might then ask ourselves, well, if it's not copper, do we have a guess on what it could be? And so we would compare to the other heat capacities we have, and based on what we're seeing, I can say, well, it's kind of close to these two. Now, copper and aluminum are certainly different colors, but it's certainly not carbon dioxide. I don't think we're going to get something that's a gas at room temperature confused with copper. So, maybe this is aluminum. Maybe it's painted. That's why we couldn't tell based on the color.